I have a very good solution for that problem with my children. It's illegal, but it works. Uh, all right, I'm serious. Well, the best for last, maybe not, but really, really good. I'm sure that we're going to end on three really interesting topics. So first, I'm going to ask Deane Gudsell to join us and talk about this topic that I can't seem to get my head around, but I'm sure you're going to make sense out of it.
Thanks very much, Tim. What I want to talk about today is VPO, the facts versus the misconceptions. So there'll be some overlap to the previous talk by Sam, but we'll try to get past those quite quickly. But first of all, just by way of introduction, who are we? This brand is maybe confusing everybody when they see my business card. Amp Control owns the company called Captech, whose brand you see here, and whose voltage power optimisation and power factor correction you'll been looking at over the last day. Captech is owned by Amp Control, and we're an Australian-owned, privately held company with international subsidiaries. We're an electrical and electronic manufacturer and service provider since the 1960s. It's a Newcastle-based company, that's where the headquarters are, and we have facilities in pretty much every state of Australia, as well as in the UK, Russia, South Africa, including manufacturing facilities in those countries. We're about $250 million a year turnover, 150 engineers and about 600 technicians in Australia. So you can see, why am I telling you that? Just so you understand, we're a fairly substantial company and very proudly Australian and manufacturing in Australia, even though sometimes we do distribute product that's not manufactured in Australia. They acquired Captech in mid-2013. So Captech, we are a specialist power quality and energy saving and equipment manufacturer and services company. We've been the market leader in, or one of the market leaders at least, in power factor correction, manufacture and supply in Australia for 30 plus years. We've introduced the European manufactured Ortia VPO, or voltage power optimizer, to our range in 2013. And just, you would not have heard of Ortia, I'm sure, before. Ortia, as I say, are an Italian manufacturer, and they've been manufacturing voltage stabilisers and voltage optimisers now for decades. Again, just from a credibility perspective, to give you some idea of our customer base, I suppose you can't have been in business in Australia and, as we say, a market leader if you haven't sold to a lot of the largest and most prominent brands in Australia. Myself, just because I'm going to tell you some things that are sometimes provocative, just ask Klaus. I'm an electrical engineer, had the first 20 years of my career as a power supply engineer and ended up senior manager at an organisation that some of you would know, which is now called Ausgrid, but I'm back in the Energy Australia days and before that the County Council era. Then followed that on with 20 years in the energy efficiency field, in energy performance contracting and now in provision of power quality solutions, including power factor correction and voltage optimisation. I've delivered many large energy performance contracts to hospitals and hotels and councils over my career. I had over 10 years on the Australian board of the Australasian Energy Performance Contractors Association on the board, and I've implemented many VPO solutions, voltage power optimisation solutions, for supermarkets, office buildings and hotels. So let's get into what really matters, not me telling you about me and the company. Some common beliefs, and effectively this is a shopping list of the things I'm going to talk about. But rather than that, I thought I'd throw them out there as these are the things that people have some misconception about in the marketplace, and that things like the supply voltage is 240 volts, and if it's not 240 volts, there's a problem. And I've had electricians contact me to say, it's 220 volts, there's a major problem here. when that was actually the design voltage. That it's constant, that the three-phase supply is a balanced supply. It's not always. Motors are designed for optimum performance at 240 volts. Reducing below 240 volts will increase the current and burn out my motors. So we're going to address all of these issues, and rather than keep reading them, I'll move on because I know time is short. So the first one on supply voltage, and this was touched on by Sam. There's an Australian standard that changed in the year 2000. Prior to 2000, the Australian supply standard for the guys where I worked was 240 volts plus or minus 6%. Changed in the year 2000 to 230 volts plus 10% minus 6%. So that means in the range of 254 volts when we're measuring line to neutral to 216 volts, the Ausgrids, Energex, Essential Energies are all quite legitimately supply you at whatever voltage in that range they like at the metering point, at your main switchboard. And then AS3000 comes in and there's another potential 5% voltage drop within your facilities. In reality, manufacturers of the equipment that you use actually design for that. So if you go to the NEMA website, you'll find they talk about motors, for instance, being designed for plus or minus 10% of the nameplate voltage to operate normally. Doesn't necessarily mean that's optimum though. 247 volts is the most commonly recorded average supply voltage that I have seen. Sometimes I've seen average voltages of 254 volts and 255 volts. And one VPO, when installing it on commissioning day, it was 259 volts. So you can see that quite often voltages in Australia can be quite large. They can also fluctuate quite a lot, as you can see from the red graph on the bottom here. That's not untypical for the voltage to vary, and I think you can see that one there is up at 254, but yet we've got dips down to 236. I've seen them down to 229. I've seen them to 186 as well. We've already had a definition of what voltage optimisation is, or voltage power optimisation. Both terms are used. It's a reduction in the balancing in the electricity supply voltage to achieve really an optimisation of the performance of your electrical equipment, with the outcome of saving in energy consumption and a reduction in your maximum demand. So now some absolute facts. Optimisation of supply voltage amplitude will normally reduce energy consumption of inductive loads, motors in particular. Also magnetically ballasted lighting, if there's any still out there that's not being changed out. The reduction varies depending on the average reduction in the voltage that's achieved, the stability of the reduced voltage, the ability to balance the phase voltages, and we'll address some of these in a moment, and the type of electrical equipment connected. It is not the same as power factor correction. And to that point, I thought I'd throw up a slide just to show the way that the two devices can be connected on your main switchboard. So here you'll see the VPO is in line with the main switchboard and all the loads. So all of the power, all the current is going through the device. Power factor correction device is installed down here, but controlled via the CTs after the meter. So it's a parallel device. It's not having all the current go through it. It's adjusting the voltage. Well, we'll get into what it's doing in a moment. Getting ahead of myself. Now, alternately, and I was talking to a gentleman a little while ago with a hotel where a lot of this is going to be voltage insensitive. So really it's going to make more sense to put this down here, just on the load that it's going to influence to get the best return on investment possible for that site. Very quickly, the difference between power factor correction and VPO, and this is relatively high level layman's term type stuff. We all know AC power is a sine wave. I've shown two sine waves here, one for voltage, one for current. And this is for a site that's got, and I haven't tried to quantify these numbers for you. We've got an out of synchronisation, we'll call it, between the current and the voltage waveform with poor power factor. And power factor is effectively the difference between those two. It's not vectorially, but for the purposes of this, that's what it is. When we install power factor correction or capacitance, which is the opposite of a motor and inductance, and it's the motors that are causing most of this bad power factor, then we tend to bring these two waveforms into alignment, maybe not as perfectly as I've shown there, but that's the objective. But the other thing that happens is you'll notice that the current has reduced. So it's an opportunity to improve the capacity of a switchboard, as well as to reduce the demand charges where you've got a kVA maximum demand charge. Now VPO, the same input, current lagging the voltage. By its nature, and we'd have to go through vector analysis, but it's because the VPO works best on the inductive loads. So it's actually allowing this lagging current to catch up a bit, not entirely. And you heard Sam say that they've seen up to 20% improvement in power factor by implementing voltage optimisation. But what we're doing is we're actually reducing the voltage waveform. So you can see here we've reduced the amplitude. We will also reduce the current to some degree, but they are a different thing and they do it in a different way. And here's what it would look like if you did both. Now, if you've got really bad power factor, you should be considering power factor correction. If the power factor is not too bad, VPO may well be all that you need, but they do different things. And here I've highlighted the difference really, and that is that the voltage optimisation will still improve the power factor to some extent. It will reduce the maximum demand, and in fact it will reduce it by a larger percentage than it will reduce the kilowatt maximum demand. But you're getting your energy consumption savings and extended equipment life, which we'll talk about in a moment. Rules of thumb, HVAC and refrigeration are the sweet spot for VPO, and by that I mean you get your best return on investment out of those loads, where those loads are dominant. Saving will vary based on the design voltage for the motor and the load. As a generalisation, variable speed drives will reduce but not eliminate the level of saving for motors. Inverter air conditioning, like Deane VRV, no energy savings. Just look at their nameplate, it even tells you on there. And as a generalisation again, electronic or switch mode power supplies like those with IT, electronic lighting, electronic supplied lighting, no energy savings by reducing voltage. And here's a representation of some test results that I've carried out, as well as customer data from sub-metering. And I've put the stars on those that would be probably the equipment that the audience would be most interested in, being HVACR. So we've got pump motors, fan motors, packaged HVAC, refrigeration, commercial refrigeration, and these here are the older forms of lighting. Of interest, you'll see here that VSDs I've shown. Now I've got some max and mins here because it depends on what you're going to achieve. But these are around about the 10% voltage reduction and the sort of level of performance you'd see. So you see here I've got for a commercial refrigeration site a 15% energy saving for a 10% reduction in voltage. That would be assuming it's a 380 volt nominal rated motor. And in fact, I'm a conservative and it's 17% I'm seeing in the field. But we use, and I'm sure my competitors use, similar information to this to estimate for our clients the energy savings we're likely to see by the implementation of voltage optimisation. So really this is a restatement of the same thing, but when we go to a site to do a site survey, for one of the things we also like to find out is if there's been an energy audit, what's the split up of the loads? If not, we have to work that out for ourselves when we're there, so that we can then apply. Here we're showing refrigeration of 52% in a particular supermarket, so we'd go 52% of the kilowatt hours times, let's say we're getting a 10% reduction in voltage. Before you saw on the slide it's about a 15% reduction in energy for the refrigeration motor, so it'd be 15% of 52% of the total kilowatt hours for the site, just as one example of the process we go through for calculating what energy savings might be. Again, with refrigeration, I know that's not the whole game here today. We're also talking about air conditioning, somewhat similar systems. A commercial refrigeration site at a supermarket where we've got sub-metering. This is raw data. This is 100 days before installation, and then 100 days, a year later, the exact same 100 days, but without taking weather into account in this instance. Now, when we tally up the total kilowatt hours, we were 17% energy saving. The reason why we've got some of these where the red line, which is the after line, are above the previous line is weather conditions changed. So we then looked at the whole supermarket that refrigeration load was at, and we ended up with a 12.3% energy saving when we just looked at the raw data again, without adjustment for weather data. This is just the raw data. So at a 12.3%, you can see the red line is the after, the blue stuff is the before kilowatt hours. That's a full year's worth of data both ways. But then when we do a linear regression analysis in accordance with the IPMVP, taking into account the weather variables, heating degree days, cooling degree days, and humidity, the actual energy saving went up slightly compared to the raw data because the weather conditions were hotter since the unit had been installed, and it's now at 13%. So here, this is the data before, the model, the regression model, which adjusts every day as we go forward, and here's the actual energy consumption after the unit was installed. Common beliefs. Motor's always designed for 240, we talked about earlier. Reducing voltage will burn out my motor. Unbalanced phase voltage doesn't hurt my motor. So let's talk about them. First one, sometimes true. Second one, depends. And third one is, well, just straight wrong. So here I've got circled on a Bitzer refrigeration compressor motor, just because most of you probably never look at the nameplate on an electric motor, and I didn't before I got into VPO game either. It's amazing how many motors are actually designed for 380 volts as their optimum performance level. There's still 415 volt motors nameplated out there, although often it'll be nameplated on the outside of a packaged unit or something, and you open the door and have a look at the compressors, and guess what? It'll be 380 volts. It's surprising how often you find that. But it is something we've got to watch for, because sometimes motors can be at a higher level. And we'll see some performance graphs in a moment about why we're cautious about that. But basically, by knowing this, and this helps us in our prediction of what the energy savings are, and in some instances, whether in fact we should be doing voltage optimization for that particular motor. That's quite a rare occurrence where you wouldn't, because mostly they're 380 to 415 volt motors. I mentioned before NEMA and the 10 plus or minus 10%, but they also stipulate that the limit to unbalanced voltage they would recommend to be as low as 1% between phases. Your supply authority typically is looking at 2%. Now this is, I know it's a little complicated, and I'm going to go to a simpler one in a moment. And this is in my paper, and I'm more than happy to send it to any of you if you'd like to give me your information later on. I can email this through. The main two curves here that I wanted to point out, so we've got voltage variance below. The design voltage is the 0, 10% above. So let's go up and hit the power factor curve for this particular motor. You can see here the power factor has reduced by 10%. It's 10% worse at a higher voltage. Now, if this is a 380 volt motor, that's 245, 247, which we normally see. It's got a 10% worse power factor than it should have at its design level. And in fact, as you reduce the voltage, the power factor improves. But also notice this, it's almost, I'll call it a bathtub or a U-curve for the current. And you'll notice that it's almost at its minimum at the design voltage, but at that 247 volts, it's actually about 4%, 3.5%, 4% higher than it is down here. And you'll see though, if you do drop your voltage too low, yes, the current will increase, but it'll actually increase if you go too high as well. Now here's some of my own data. Similar thing, design voltage is 220 volts. You'll see up here that at 247 volts, we've got 5% more current. but we've got 17% more kVA. And this is where many of the motors out in the marketplace are actually designed for, and this is the voltage they're seeing. Look, this is just to show you that unbalance does occur as well. This is an example of an installation I've done in the past. You can see that this particular voltage optimizer stabilizer has reduced this unbalance significantly, and that's around about a 2% unbalance. So let's have a brief chat on voltage unbalance. I'll just go to the example, and you can read the rest anyway because I'm going to take up too much time. You'll see here that for an average voltage of 230 volts with a 2.3% unbalance between the phases, so A to B, B to C, whatever, just with a 2.3 variance, we've got a 17.7% unbalanced current. We've got a 30-degree temperature rise in the motor. It's not a good scenario, especially when, according to the motor manufacturers and the paper Klaus has got, winding insulation life is approximately half for every 10 degrees C increase. We just saw potential 30-degree increase from a 2% voltage unbalance. And we saw an example of a site where it had that. Motor losses increased 25% with a 4% unbalanced voltage, as you can see down here. And I've had to highlight a pen on these because they were black and whites. Now, the references for these are in the paper. So, as I said, be very welcome to share this with any of you. So you can see here the 4%. We've got the motor heating increased by about 30%. And we're up at about 25% increase in the losses for the electric motor for unbalanced voltage. There's numerous types of VPO, and I think rather than go into any detail on this, I just ask you to have a read of it and have a think about the fact that there are different technologies, they perform differently, they deliver different results, although by and large they're designed to do the same thing. But it's like anything, you get different results from different technology or variations to a technology. Personally, I'm an advocate of the stabiliser type. Maybe that comes from my boring old power supply engineer background, but I'm also seeing that we get a lot more energy saving from a stabiliser and a fast stabiliser. This is just a quick example of the differences you can see. This is the supply voltage. This is if it were varied by 6% by a fixed tap voltage optimiser, which do exist and are a legitimate technology. And here's a stabiliser on that same input voltage. Now, these are models. Well, this one's actual. That's a model, reducing that by 6%. And the percentage voltage reduction is pretty close to linear to the percentage energy saving, depending upon the type of equipment, like we talked before. But down here, this ends up an average of about 9% energy saving versus 6%. So the average voltage is reduced by about 9%. So there's a significant further opportunity for energy saving, but I have to say, for that particular pattern of supply voltage. If that was rock steady, which you almost never see, then no, there wouldn't be such a big gap between a fixed tap voltage reduction and a stabiliser type. As I said though, I'm an advocate for the stabilisers because I've got a power supply background. Getting close to the finish, so energy bill savings of the order of 10 to 15%, but that's where there's a predominance of refrigeration or HVAC equipment, and particularly if it's 24/7 operation. Return on investment we see in the marketplace, and it depends on what they're paying for their electricity, of course, and how difficult the installation is, of the order of 2 to 4 years simple payback. I did one yesterday for a food manufacturer that's 1.9 year simple payback. Just happens to be their load profile really suited it. And that's the equivalent of 25 to 50% return on investment. So you can see it's not a bad return on investment. I suppose I should put in a little sales pitch. So our particular unit can sustain input voltages of between 254 and 220 volts and deliver a 220 volt steady output with a 0.5% accuracy. Now, it can handle voltages higher and lower. It's just that this 220 may vary a little, depending on how big a change there is in the voltage outside that range. But certainly, that's all within the range and that we'd normally expect to see. We also have, and sorry, I should also mention, it's a very fast unit with 16 milliseconds. It's 0.016 seconds response time, where it actually adjusts the voltage. We have independent phase and automatic phase control, so that each phase is adjusting independently. We have surge protection, and importantly, and particularly for refrigeration loads, I just insist that they go in, we have a bypass switch, so a physical bypass can take place of the unit for either maintenance or repair if that was ever required, or for whatever reason that the customer decided that they needed it out of circuit, rather than have to go through another power interruption. We have input-output display like they pretty much all do, but there are optional other stabilisers that can have as much as plus or minus 30% fluctuation in the input voltage to maintain a steady output. The predominant one, though, that we're offering is this one. I would suggest that you've got to look beyond the technology, though, and I'm sure that you're all acquainted with that there are build quality, reliability, track record of the equipment, whether it be in Australia or overseas, the stability of the voltage output, the speed, the independent phase control, and I really think the last two I can't stress enough, because I've seen a few VPO businesses and power factor correction businesses come and go, and people jump on the bandwagon. Have a look at the technical support that's offered in Australia. Is it one engineer they've got? Is it 100 engineers they've got? And look at their business strength. Are they going to be around in 15 years when they're offering a 15-year warranty? Have they been around for 15 years? I just would suggest that you look at those. Effectively, I'm finished. And I wanted to finish really on the common beliefs and whether they're right or wrong. Thank you very much.